Well, good evening, friends. Welcome to the introductory meeting and presentation for the brand new Natural Sciences Club of Southborough. Ooh, excellent. My name is Susan Heilman. My pronouns are she, her, hers, and I am the newly appointed president of our Natural Sciences Club of Southborough. So the way this came to be is a group of us that were interested in sciences in Southborough. We had coffee over various times, we're meeting, kind of hanging out, talking about various issues around Southborough that happen to have a common denominator of natural sciences. And we thought, hey, why not a natural sciences club? I wasn't even there for the initial meeting, and my husband said, oh, Susan will be president, it'll be great. And so here we are. But the other people that are kind of my partners in crime with all of this is my husband, Destin Heilman. You'll hear in just a moment giving our talk. Freddie Gillespie is over there waving a hand. Amy Cassetley is right up front, and Jenny Pete also back over there. So if you have any questions about this new club, but we have a lovely Facebook page. Some of you have been invited to that. If you're interested in searching for Natural Sciences Club of Southborough, and then I'll approve you and you'll learn more about some of the things we're going to do. But what we'd like to focus on is not just the natural sciences themselves, but the fact that, so for example, we're going to talk about dark skies and learning more about astronomy and the very expensive hobby that my husband decided to take up. But it's not just about looking at doing the astronomy, looking at that and the beautiful pictures, but it actually has something to do with Southborough down here, because dark skies aren't always easy to come by. In Boston, they're very hard to come by. Southborough's a little bit better, going further out rural, it's a little bit better than that. But there's some things that we might have to be concerned with, that maybe our dark skies aren't going to be as dark as they once were. And so that's something that as a community we can think about, and as individuals we can think about. And so we'll talk a little bit more about that towards the end of his presentation. We're interested in things like mosquitoes that spread disease, but how do we get rid of those mosquitoes and not harm our environment at the same time, and also not be as worried about the diseases that they might carry? And so we're planning on future talks thinking more about that. Along those same lines, I've always wanted to build a bat box. Bats are incredibly amazing animals to have around, especially if you're concerned about mosquitoes. So why not have the Natural Sciences Club come together? We'll build a few bat boxes. That would be fun to put around our homes. So there's lots of different places we can go. There are literally miles of trails in Southborough alone that I don't even realize, and part of our community is supporting them. Eagle Scouts go out and clean them up and build bridges for us. And we have Chestnut Hill Farm that's got acres and acres of natural habitat there. So Southborough has a lot of natural sciences to give, and our club wants to be able to explore that and explore that with all of you. And we're going to start with taking a tour of the skies, which obviously don't just belong to Southborough, but things that we've seen just from Southborough. So now I'd like to introduce my husband, Dr. Destin Heilman. He's a professor of biochemistry at Worcester Polytechnic Institute. And as I mentioned before, he has this lovely and engaging hobby of astrophotography. So he's going to talk a little bit about some of the many telescopes he has, the observatory that's in our own backyard, and some of the amazing pictures that he's taken, and that he'll give you a better view of some of those. So please join me in welcoming Destin Heilman.
Thanks. I don't usually like using mics, but I'm going to try because I had 4 hours of lecture today and 2 hours of office hours after that. So my voice is really tired. Is this on? Is it good? I have to hold it really close. Okay. Hi.
Hello,
Thanks for coming. I am delighted to share this with you. I've been sort of tucked away at my house in Southborough doing this for many years, and I don't talk about it much. Maybe some neighbors, right, that I see kind of curious about what I do. So I'm delighted to be talking about this, especially since I do all this from Southborough. Southborough does boast some great dark skies, comparatively speaking. And there is a danger that could be going away. And so I'm particularly sensitive to that, but I want to make you sensitive to that too. And that would be great. So I'm also a trustee of the Southborough Open Land Foundation. I'm all about conservation, including conservation of dark skies. There's a lot of things that we can talk about, with respect to light pollution that impact the environment and impact our own health, which I'm going to get to at the end. But let's have some fun. If I can find my clicker. I don't know where the clicker went to. Here it is. Okay. Okay. Let me show you where you live. This might be a surprise to you. But before I do, you're going to see some distance markers on here. There are these little circles that fly in and out. And every time you see a circle fly by you, it means it's 10 times the distance it was before. Okay? Okay. You live on Earth. I hope you know that, right? It's a small blue planet in the middle of nowhere. We have one moon that circles around us. We are in a solar system, right? You probably know that part too. How many planets? Yeah, depends, right? It depends. Okay. Here's our solar system. It's around a pretty boring G2 class yellow dwarf star, but that's good. Boring is good for us. Our solar system exists in the Orion arm, the Orion spur of the Milky Way galaxy, which is a collection of hundreds of billions of stars. And now we know from the Kepler mission that almost every one of those has a planet around it. Our galaxy is part of a cluster of galaxies we call the local group. And the local group of galaxies is part of a supercluster, we call it. It's called the Virgo supercluster, that is a lot more galaxies that are in there. That supercluster nestles together with a bunch of other superclusters of galaxies that then form up these giant galactic filaments that fill up our entire universe. It's a big backyard. And we can actually see a lot of stuff in it. Let me show you what we can do. But first, I need to redefine astronomy for you. Looking at impossibly dim objects shrouded by blanketing darkness with feeble human eyeballs. And I'm going to prove to you why they're feeble. In order to look at anything from stars to galaxies and stuff like that, we usually have to use one of these. Telescope's basically a light bucket. It's going to gather more light than your eyeball can gather, and it's going to funnel it into your eye. Even if it does that, though, we have a problem. So here's the making of eyeballs, right? Here's the anatomy of an eyeball. I'm going to give you a crash course. Light goes through the cornea, through the pupil of your eye, and it hits this thing in the back called the retina. The retina's got all these cells in it that can detect light. There's two types. There's rods and cones. The cones are the ones that are great for us. Those are the ones that let us detect bright light. Those are the ones that give us color detection. They're the ones that give us 20/20 vision. The rods that are there, those are the ones that are good for dim light. So we've got those all over the retina. We can detect dim light, but we only have about 2200 vision with the rods. Now there's this interesting little thing right at the back of your retina. You'll notice it's right in back of the pupil and the iris. There's a little depression right there. It's not labeled on here. It's called the fovea. The fovea is directly behind your retina. Anything you look directly at, light goes right on the fovea. And so the interesting part is it's completely packed with cones, no rods. So in addition to us having these rod cells that detect dim light but not so well, that give us horrible resolution, when you look directly at something that's dim, you can't see it because you don't have any rods in that area of the fovea. So you have to look not directly on it in order to see it. Astronomers call it averted vision. So you have to get used to looking at stuff through a telescope but not directly at it. It's a ridiculously futile exercise, right? So best case, you're going to be not looking directly at an object. You're going to see this fuzzy object, and as soon as you look at it, it sort of disappears, right? It's this crazy effect. And you can't be looking right at it, and even that sort of peripheral vision you're getting at it, you're going to get 2200 tops. So that's why I like to take pictures, because these are not the best thing to look at the sky with. There are a lot of people that would be angry about that, right? Astronomers that like to do that stuff all the time. I like to look visually. There's something special about light having traveled hundreds of millions of light years just to fall on your retina so you can barely see something, right? Okay. I'm not biased or anything, though. Okay, so if this is Percival Lowell, the Lowell Observatory, this is where Pluto was discovered. If you're looking through a gigantic light bucket like the Clark refractor, you're going to see a faint fuzzy, right? On a good day, by averted vision, not looking directly at it. So that'd be a galaxy. If you happen to have a little bit better telescope, if you've got something orbiting in space, then you can do something like this. This is the Hubble Deep Field, where you can see gobs of galaxies, gobs and gobs and gobs, where the director's discretionary time, which is 4 days worth of time, was pointed at a seemingly empty part of space. He said if this didn't work out for anything, he would have gotten fired for this stuff. So he would have gotten fired. Pointed at the Hubble telescope for 4 days of exposure time, and this is what we get. It's one of the ways that we learned that our universe is teeming with galaxies. Here's another one. This one's called the Coma Cluster. And everything that you're seeing from top to bottom, sort of in the whole middle, is all galaxies. There's a few punctuated stars and stars to the outside. These ones are all yellow. There's a little spiral guy at the bottom. These ones are yellow because these are very, very old galaxies. These are elliptical galaxies. The Hubble didn't take this one. I did. So we can do stuff like this in our backyard. I'm going to show you how, if you're interested, right? So 3 things to get started. The first thing you need is a telescope, but you can do this with a lens. You can take great Milky Way shots with lenses. So 3 types, and here's the most important things. How easy are they to use? How expensive are they, right? So refractors are the types of telescopes that you're very used to seeing. These are ones with lenses in the front. The light enters the front, hits usually a diagonal, although you don't need one, and goes up into an eyepiece where it focuses on your eye. So those are great. They're hideously expensive, but they're really easy to use. So you can throw a lot of money at a problem and make it go away. A reflector is one of the most budget options we have. Here's 2 library Loaner reflectors, which I'll talk a little bit about later, but you can take these out of the library. They're fantastic scopes, I approve. They are the cheapest, and in terms of ease of use, they're sort of in the middle. They're not so bad. So you get the biggest bang for your buck with a reflector. This is called a compound or a catadioptric telescope. It's got both mirrors and lenses, and it folds the light lots of ways. A Newtonian reflector comes in, it bounces off the primary, hits the secondary up to your eye, so it folds the light. That means it's a longer focal length. Think of telephoto lens, right? So it's a really zoomed in picture. The catadioptrics do that even more. They fold the light again and again and again. These are moderately expensive, kind of tough to use. But the weird thing is, these are the most popular. This is the one everybody wants to start with. I don't recommend that. So you get a telescope, but it's cool because nowadays, because of computer technology, because we're really good at manufacturing stuff, or at least other countries are, you can pick up a really great Newtonian computerized telescope that'll slew to different places in the sky for about 200 bucks. So it's not bad. So the second thing you need is a mount. So here's a fun fact. You might not know this. The Earth rotates. And that makes it difficult to take pictures of stuff in the sky. You can snap a really quick picture, but a lot of these pictures are going to take long exposure times. That means you sort of have to either open your lens, open your telescope up, and just make stars smear all over the place because the Earth rotates, or you have to track along with the Earth's rotation. So a lot of times we use stuff like this. Here's the Clark refractor again, but that whole thing on the right is the mount. And this is an equatorial mount. There's a few different kinds, but the way this works is this. So you can kind of do this exercise a little easier than I can. We'll do it together. So you see this part right here where the telescope kind of hooks up. Here's weights to counterbalance it, but there's this wheel right here. I want you to imagine that that can turn on that wheel back and forth there. And they can also pivot this thing up and down in the observatory. So I want you to imagine that you're the Earth, and you're going to lean back because you're kind of at an angle, right? The Earth's tilted, and the top of your head is going to point right out toward your rotational axis. So it's kind of like you're rolling around like this. That thing has to be pointed right towards where the Earth is rotating. And if they get it just right, if this axis right here is pointed right towards the Earth's rotational axis, all they have to do is let this thing swing around at the right rate, and it'll track perfectly with the sky, regardless of where they point it. Now here's the million-dollar question. You're the Earth. You're tilted back this way. The axis of rotation is that way. Which way do you turn? That's the right way. Sun rises in the east, sets in the west, right? So the sky moves this way, which means the Earth moves that way. So you move left. You rotate left if the top is the North Pole. Okay. You've got your telescope, you've got your mount, and we're looking for a better sensor, something better than your eyeballs. You can start out with something like this, right? My 2007 picture of an iPhone, right? It's called afocal astrophotography. You just park a cell phone right down in the eyepiece and you can try to take a picture. It's actually a legitimate way to take pictures. They've even got these doohickeys where you can park your cell phone in there and it's a lot easier to align. It's got little knobs you turn and you can line it up. You got to try this, it's fun. With that and a little bit of help from some computer software, not much, you can get pictures like this. So the moon pictures are the easiest ones, right? But you can pictures of Saturn and Jupiter that look like that. Those were taken by a cell phone, right? Little bit of software to help you with that. It's pretty much you take a bunch of those pictures or a movie, you dump into the software, you crunch it all together, and it spits out these beautiful pictures. If you want to know more, I'll be happy to tell you about how to do that. And I just labeled the Apollo 11 moon landing site because it's the 50th anniversary. Yay! Okay. So here are my rigs. My wife loves this part. It's her favorite part. I have lots of them, right? And there's a legitimate reason for this, right? I tried to convince her of this. You can't zoom in on a telescope. That doesn't work. You get a certain image field, a certain field of view, and that's what you get. So in order to get different fields of view, if you want wide field, narrow field, stuff like that, you got to buy another telescope. That's why you have to do it. So these are the rough fields of view. You can be really zoomed in. These are actual fields for these telescopes. And so you can get everything where this is about, everything about half a degree or so, which is the moon just completely filling up the picture, all the way down to something where the moon is that tiny and you get a larger field of view. You can go even wider or even narrow with this. These are just the ones I have. But it's really necessary because things in deep space especially are all different sizes. And you want to be able to get up close. Now all the alignment, these mounts that I've got are the same class as they have in the Clark refractor. They've got that axis of rotation. It's got to point right toward the Earth's rotational axis. But that gets really tiring. So I got tired of sort of going out in the yard, taking an hour to set up the scope, perfectly align it to the pole, and then get the whole thing started. Fire up the computer, yada, yada. So that's when I decided to build an observatory a few years ago. So it just sits there. I just open it up and then start taking pictures. And so I didn't want it to look like an observatory, though. I don't know why. I didn't want the big dome and all that stuff. Sometimes they're more trouble than they're worth. So I made it look like a little tool shed, and then you just push the top back, and the telescope rises up out of the inside. So it's kind of like a surprise, right? So that's actually what's in the backyard. Everybody asks me, why do you have two tool sheds? It's like, okay. I like tool sheds.
I like the flowers.
Yeah, the flower boxes, yeah. Yes, that was Susan's contribution. So here's a zoom in of one of these telescopes. You can ignore most of the stuff here. This is USB hubs and cables and stuff just to connect the cameras. Most of this stuff is completely superfluous. This is a DSLR camera. You can go over to Best Buy and buy one of those. This is one of Celestron's mid-rate Cassegrain telescopes. And there's an adapter you use just so that the camera can go right through the telescope to take pictures. Then you just snap away. You can do this with an intervalometer. I'll show you how to do that. But I want to focus just really quickly on this part. There's actually a second camera and a second little tiny telescope that can ride piggyback on this. And it's called a guiding setup. So it turns out to do like long exposure photography. So instead of snapping a picture for 20 seconds, you want to do one for 20 minutes. You've got to guide a lot more accurately than this mount can do. There's mechanical imperfections and stuff that make it pretty poor. So what you can do is attach a second camera and run a free piece of software. It's great. Some scientist out in California wrote this because he likes the hobby. And all it does is it puts crosshairs on a star, and every time your mount starts to drift off of its position it's supposed to be on, it issues these little corrections. Just bumps the mount and pushes it back. This is incredible. This is what you used to have to buy a mount that was upwards of $10,000 to get this kind of guiding. But with a really cheap mount and some free software, you can get it guiding like it's a $10,000 mount. So it's really cool. It's made everybody able to burst into this hobby and not have this huge monetary mountain to get over. There's still some monetary mountain, but not as much. All you got to do is put your intervalometer in there, and the only reason for that is just because if you push the button on the camera, it's going to wiggle the telescope, so you don't want to touch it. So you just have a cable, you hit the shutter, you can program it to take pictures. There's also computer software you can do that with if you don't want to bother with the intervalometer. And it's fun because you can watch the pictures come down, and then you snap away. They're called sub-exposures. So the idea is we're not going to do what Hubble does. We're not going to take a picture that's 4 days long, right? We can't do that. We're going to take lots and lots and lots of snapshots, anything from 5 to 20 minutes, and then we're going to combine them all. And there's a specific reason for that I'll talk about in a second. It's called stacking. But before we do that, you have to calibrate these pictures. You ever taken a picture at night, or like you're on a cruise ship or something, and you snap a picture and it's just grainy everywhere? That's thermal noise on the chip. These chips are noisy. There's a lot of photoelectrons that are generated from just the act of taking the picture. And when you take a really dark picture, most of it's noise. So you can get rid of that stuff with these calibration frames. The darks get rid of the thermal noise. The bias gets rid of the chip noise, and then the flats correct for vignetting because it's not an even flat field. All this is to say is you can get rid of the noise if you go through the right processes. You can take the nice cruise ship photo and turn it into a less crappy cruise ship photo, right? Okay. This is what a really zoomed in view of a galaxy looks like in one of these pictures. It's super duper zoomed in, and I did that so that you can actually see the pixels. Can you see them? So this looks like a distorted blob because it's a really distant background galaxy. This is a foreground star. And I want you to see what the calibrations do. So this is what you do when you dark subtract. You take the thermal noise off the chip. It just goes like that. Now I'll run that back and forth. But look at some of these pixels that are up here. Those are not pixels that are supposed to be activated. Those are hot pixels, thermal pixels that come out. So you can see what this does. It smooths out the background. It takes a lot of the other light away. That's just because when you do this, the picture actually gets a lot darker. So that's the dark subtraction. It's really subtle, but it's super important. Then you're going to do the bias and the flats, and then you're going to stack them. This is where it gets fun. So what you do is you grab a free piece of software. There's one called Deep Sky Stacker everybody loves. You download it, you dump all your pictures into it, and it does this automatically. It finds all the stars in your image. And because you've been taking all these snapshots, the odds of you not having moved around the sky is pretty low. And it's going to align all of these pictures according to their stars. It realigns all of them. Now that is a really subtle thing that happens, but it's super important. All the noise that's on the chip that's always in the same place, it gets shifted to different positions now when you do this. And that means when it stacks, it can statistically subtract all the noise, or at least most of it, lots of it, out of there. And the more sub-pictures you have, the more noise that comes out. So we stack those, and this is what you get. So this is the dark subtracted one, and this is what happens if you stack about 50 of these together. You get that. So it's a huge difference. You go from this grainy, pixelated thing, and then you can't barely even see the pixels because it's so uniform. The background's nice and smooth, and you can start drawing up. Then you can actually start to tell that that's a galaxy. You can see the spiral arms, little dust clouds and stuff on it. So it's kind of fun to do because it's free software and it's really easy. You just dump it in there, it does all the hard work for you. Okay, now this is the really fun part. Because after you're done with that, you're just going to get this black and white image that barely has any color in it at all. And you have to do a lot more work. So after about 6.5 hours of pointing my telescope at the Andromeda Galaxy, this is what you get after stacking. It's like, well, that's terrible. There's nothing there. But if you do some post-processing, so this is where you use a program, everything from Paint to iPhoto to Photoshop. I like to use Photoshop. You're going to suppress the dark parts, and you're going to draw out the bright parts. And then one stretch of that gets you this. And you do it again. And then you start adjusting the image, and there's lots of little tricks that you learn. This is the tough part to learn how to do. But lots of little tricks that you learn where you can selectively add curves and pull out the bright parts. Then the color starts to go awry because you use a light pollution filter. So it turns green, but we can correct for that. You just adjust the colors to what they're supposed to be. And then you brighten it up. You can make the dust lanes darker. You can do all these things that your eyeball would not do because this is not what you'd see. If you were right outside of the Andromeda Galaxy, it would still be very, very, very dim if you were orbiting right outside its boundary. So this is what we have to do in order to see this. This is not what you'd see if you were orbiting around the Andromeda Galaxy. It's just that dim. But it makes for a pretty fun picture anyway. So you do some more adjustments and that kind of stuff, and you end up with a final picture. But it takes a lot of post-processing. So ordinarily for a picture, for 6.5 hours of exposure, anywhere from 10, some of the ones I'm doing now are up to 40 hours of exposure time. It usually takes an equal amount of time post-processing for every hour that I put in exposure time. So it's a lot of time that goes into making these. But it's super fun. My wife always knows where I'm at. On the computer processing. So here's just the zoom in so you can see the core of the galaxies, nice little spiraling dust lanes that go around, stuff like that. Okay, so let's get to the tour. So this is deep space and a DSLR. So the vast majority, these not every single one, but the vast majority is taken with a DSLR camera and an intervalometer or a computer program. So here's that Coma Cluster, and I've got to cheat a little bit because I've got some notes up here because I can't remember how many light years away. This is 320 million light years away. So if you, let me give you a guttural feel for this. If you got into your car and you got on the Mass Pike over in Framingham and you took off going down the Mass Pike at 670 million miles an hour, right? You don't have to worry about the cops. 670 million miles per hour, that's the speed of light. It would still take you 320 million years to get to these galaxies. It's kind of far away. And it's also one of the reasons why they're kind of blurry and you can't see a lot of features, but I'm always totally psyched and you can actually make out little spiral structures in some of these. And I have a lot of fun just zooming in and looking at all these little faint fuzzies. There's just galaxies everywhere if you zoom in, little tiny ones that are there. So what I'm going to do is we're going to start far away, and we're going to get a lot closer. This one is 45 million light years away. And a lot of them have these catalog names, NGC 4725, whatever. This is called a Seyfert Galaxy. It's actually got this amazing active black hole that's gobbling up gas in the middle of it, and it's one of the reasons why the core is so bright. But this is a really weird galaxy. I wanted to take a picture of this because it's one of the few we can easily visualize where it's only got one spiral arm. It just spirals all the way around. Little tiny faint fuzzies like that. These are 36 million light years away. This is called the Leo trio. So that galaxy right here is the one that we were looking at really close up. This one's called the Hamburger Galaxy. Right, yeah. It does, and that's why they call it that, right? So some of them have these great names. This one has no name, but I like to call it the Dali Galaxy because it looks like that melted clock from some of the Dali stuff. But if you look up in Leo with a set of binoculars and you look right under the lion's belly, you can see these three faint fuzzies right in binoculars. They're bright enough, and you can catch these. But they've got amazing color if you enhance it enough. And these are calibrated colors. These colors actually exist in the galaxies, but they're just enhanced so they look a lot brighter on the pictures. Because why not make them pretty? This is one of my favorites. I just love this little galaxy. It was a field, and this is the only galaxy that's large in it. This one's 30 million light years, so we're getting closer to home. But it's got this beautiful spiral structure to it, these dust lanes, even though it's so far away. This galaxy is bigger than Andromeda. Andromeda is our nearest neighbor. It's 2.5 million light years away. And it's a big galaxy. This one's even bigger. So it's a massive galaxy, but it's just so pristine. There's just nothing, it's untouched. Okay, so now we're getting closer. This is 25 million light years away. Now we're in our local group. So this is a galaxy that's part of our local group. It's M106. I wanted to take a picture of this one because it is a beast. This thing is a terrifying galaxy to get near. This has a supermassive black hole in its center. Most galaxies have those. But this one is extra large. These things spin, the black holes spin, and they gobble up gas, and this one likes to do that. But this one's actually on an angle, a really severe angle. So the black holes spin, it shoots out these jets of radiation from its poles, except the poles are pointed into the galaxy. So what you get, you can barely see it, but you see this little red flare coming up out of the galaxy that way? Yes. That's what I wanted to get. I took this picture just because I wanted that. That is a jet of hydrogen that's being forced out of the galaxy by that black hole's polar jets that are forcing it into the galaxy. There's one on the other side, but it's barely perceptible. I couldn't get it very well, but there's one shooting out this way. Sometimes I just want to go after these little crazy features about that. But these are all from Southborough. I don't have to go to any crazy dark sites to do this. Because I'll show you that. I have a slide for that. Yes. How do I know it's hydrogen? That was the question. All right, we'll get to that. We're getting even closer. This is the Whirlpool Galaxy. It's 23 million light years away. It's two galaxies that are crashing together. Our Milky Way galaxy and the Andromeda Galaxy are going to crash together in a few billion years. We probably won't be here for that. But it wouldn't matter anyway because there's probably not going to be any collisions. The stars just whiff by each other as they collide. But this is M51A and B, and these are colliding together. And one of the things that happens when these two gravitational centers come together is gravity squeezes things when you get close to it. So one galaxy will squeeze the other, and then you get these blue spiral arms because blue stars are really young stars. And you know when you image a galaxy, because it's got these blue arms, that it's got a lot of gravitational squeeze to it. So it crushes all the gases together, and it makes these things. Okay, let's get closer. This is the Pinwheel Galaxy. We're 21 million light years out. This one's just beautiful because it's got great arms to get super duper dim. But again, blue arms. And so anytime the astronomers are seeing this stuff, they're looking for a galaxy that it could be interacting with. Sometimes they find it, sometimes they don't. But not all the galaxies look like that. All right, we're getting really close. 12 million light years away. This is Bodes Galaxy. These two are interacting. And again, you see the blue, but now we're starting to see a different feature. You're starting to see these little red dots that are in here. And you can see that this galaxy has sort of a red core to it. And because we're getting close enough now, this is where you're starting to see these giant nebula that are these star-forming regions. You get close enough, you can see them. Now we're really close. This is only about 3 million light years away. This is the Triangulum Galaxy. And you can see lots and lots of those red dots everywhere. In fact, this one, I think my laser pointer's starting to go, is the largest star-forming region we know of in a galaxy. It's massive. It's huge. But you can tell that it's a star-forming region. Lots of blue stars around, but the blue stars are being made from the red parts. And how do I know it's hydrogen? Because when you take a picture, it's actually that color. This is a hydrogen lamp. The hydrogen gas is so hot that it glows. It actually, electrons are lost, and when they're recaptured, it actually glows that color. So they're glowing that. This is a lamp that's full of hydrogen gas, and when I put a huge voltage through it to make it glow, that's what color it is. So that's why it's that color. That's how we know. It's one of the reasons we know that it's hydrogen. Because hydrogen's that color when you make it hot. And it's pretty accurate, right? It's that kind of iridescent pink color. So great question. Okay, so now we're going to go inside the Milky Way. And this is my fun part. I take pictures of galaxies. I don't like taking those as much because there's a lot more interesting stuff. So globular clusters. These are clusters of hundreds of thousands to millions of stars in a big ball. We don't know a lot about them. We know our galaxy alone has about 150 of these. Some galaxies have more. They're in the halo region. So imagine your galaxy is a frisbee, and you put that frisbee inside of a sphere. The halo region is above and below that frisbee, and that's where these are. We don't know why. We don't know where they came from. They could be the spoiled cores of other galaxies that are left over from our galaxy gobbling up. We don't know. But they're really curious, and they're beautiful to look at. You might know this one. So this is called an open cluster. It's a small cluster of stars. This is the Pleiades Cluster. You can see this with the naked eye. It's up near Taurus, the bowl. But one of the things I wanted to illustrate here is that you start to get this nebulosity around them. This star formation is only about 100 million years old. You think stars are billions of years old. It's only 100 million years old. They're blue stars. So if somebody's taking pictures of our galaxy, this star cluster is what's contributing to our spiral arms looking blue. And they're very blue stars, very young stars. They're going to burn out very fast. But as they're passing through the dust in our galaxy, they simply illuminate the dust and make it look blue. So that's what this is. These beautiful brush strokes are just dust that surround those stars. Anybody drive a Legacy, a Forester, or a Outback? Anybody? Okay. So you probably know the star cluster a bit better. What's the Japanese word for Pleiades? Subaru. Which is why their symbol is the stars. It's this cluster. That's what they call it. Okay, fun fact. This is a dead star. This is the guts of an exploded star. This is a supernova remnant, so this is what's left over. That's hydrogen gas, and the blue stuff is oxygen gas. And we see this really readily. It's very bright. This is something you can see visually on a telescope. It's called the Veil Nebula. If you zoom in, it's really filamentous. It's wispy. It's really pretty. Question?
I didn't know it's oxygen.
We're going to get to that. I'm going to show you. This is the Orion Nebula. So this is one that you can see with the naked eye. If you look at Orion's belt, and there's a sword that he's got hanging off of his belt, at the tip of that sword is this nebula. It's a huge star-forming region. And again, we get hydrogen gas in the middle, oxygen gas, and sort of there's also regions of the nebula that are illuminated by blue stars that are in the core. This is called the Running Man because it's supposed to look like a headless running man. I don't know what it's supposed to be, right, but whatever.
What we're seeing right there to the left of the circular thing.
This?
Yeah.
That's dust.
But it looks structural.
It is, yeah. And it's shaped by the nebula itself. So we're going to see more examples. But all of these stellar winds, all the radiation coming off of them, it sculpts the dust and the gas that's around it, which gives it this shape. So it's sort of, you get the sense that it's got a bowl shape to it.
Yeah.
And the stars are carving it out, right? That's going to be common in all of these. Yeah.
Wouldn't the elements that compose all of these systems be mixed together? Like, why do we get such banding effects?
Excellent question. Gold star. Because when the stars push them out, the elements have different mass.
Okay.
And you can push a hydrogen really easy, right? Oxygen absorbs a certain amount of kinetic energy, so they actually get collected together and pushed out like that because of their masses.
Wow.
Great question. This is the horse head, right? You can guess why. And that star right there is Alnitak. That's the leftmost star in Orion's belt. So if you look right at the leftmost star, you're not going to see this, right? Because it's too dim. In fact, you even have to have a special filter to see it. It's almost entirely hydrogen gas, but you can see these little wisps coming out of it and all that. This is just an intervening glob of dust that happens to look like that, right? Our eyes just happen to see these shapes in it. This is called the Flame Nebula. There's all kinds of little nebula around it, but it's just nice. So the vast majority of these were with DSLR. DSLRs are tough because they have this Bayer matrix in front which filters out the red, the green, the blue, and it gives a little less sensitivity to those things. So I was after an even better sensor, which of course was free, right? And this sensor is a big monochromatic sensor. It's super sensitive. But in order to get the colors, you have to put filters in front of this thing. So you got to take the color channels one by one. But my favorite part about this, and the answer is your question, it gets to your question. How do you know it's hydrogen? This is what we call narrowband. So these filters are going to block out every single form of light except this tiny little group of wavelengths of light that come in only from certain elements. So I love these filters. And so there is a hydrogen filter that's in here that only lets the light from hydrogen and it blocks out all the other elements. There's one for oxygen, one for sulfur. There's a few others. There's R, G, and B, so you can take those kind of pictures too. But this is narrowband, and it means that not only can you really block out the light pollution, but you can gather the light just from one element and say, okay, now I know that's hydrogen because it's the only one that would come through with that filter. So the way this works, it's called narrowband, is that you take separate pictures with the filters. Here's sulfur, here's hydrogen, here's oxygen. You can see how they're different. See spatially how they look different? And you get lots and lots of exposure time. So it means instead of me taking 6 or 8 hours, this is like 40 hours worth of work to get the exposure time. But they spatially separate. So this is where, as like a chemist, biochemist, I start to really geek out because I can actually see spatially where the different elements are and start to answer those questions, right? You assign them to the color channel. So some people call this false color, but we know what colors they are. We just don't make them that colors because it makes for not pretty pictures. So we make them different colors, and what we do is we combine them together, we shift the colors a little bit, and I like to use the Hubble palette. So this is exactly the way the Hubble takes pictures. It takes pictures with the same filters. In fact, the sensor I use to take this is actually the same Kodak sensor that's on the Hubble, because now it's cheap, right? It's been up there for 30 years. You can get the sensor now. So you combine these together, you get a color image, and you get narrowband. So this is what those pictures look like. And so here I can tell you positively that the rusty color, yeah, that's this one, that the rusty color is hydrogen, the yellowish color is sulfur, and the blue is the oxygen that's in there. So this is called the Rosette Nebula. It's a really big star-forming region. And this is the bowl, right? You can see here's the star cluster that formed. Once these stars formed out of the gases, gravity crushed them together, nuclear fusion started, and the radiation broke out and pushed all the gas out from around them. So they clear out the gas from their neighbors, and that's what this is doing. It's pushing these away, and the hydrogen's the lightest, so it gets pushed to the outside.
So hydrogen, I think you said that, right? So hydrogen's the lightest,
Yeah.
sulfur's the second
Yep.
lightest, and oxygen's the
Yep.
third lightest. So you can infer that it's going out.
Yeah, and it doesn't perfectly follow with mass. A lot of it has to do with the molecular composition. Is it molecular oxygen? Is it just atomic oxygen? Stuff like that.
What about the green?
The green, yeah, the green is just a color that you get when some of the colors mix together. Sometimes I don't like it, but sometimes it makes for a neat transition. But the green actually isn't anything. It's just when you put the yellow and the blue together, it makes the green, right? So here's another one. This is called the Cygnus wall. So in this case, I wanted to make the hydrogen a little bit more yellow. So this rusty color is the hydrogen, the sulfur, oxygen's over here. But this is a massive, pretty dusty region that's up in Cygnus. Lots of gas and dust. There's a massive star cluster that's right here. I can't see it because this is invisible, but you see that little tiny pink blob right there? That's the compressed hydrogen, but it's sitting behind a big dust cloud. So the Spitzer Space Telescope took a picture of this with infrared, and you can see right behind the dust that there's a star cluster there. So in a couple of million years, it'll probably break out, and somebody will see that. I'll be not here for that, but that's kind of sad. Here's the Jellyfish Nebula. This is a supernova remnant again, so you can see how filamentous it is, and why I guess they call it the Jellyfish Nebula for that. This is one of my absolute favorites. It's called Setterblad 214. Yeah, that's that one. Setterblad 214. Some of these don't have great names, but it's a great region. It's got this nice bowl to it. It's got all the different gases. It's got dust all over the place. It's just great to pick up. One of my favorite parts of this is it's got pillars. Pillars are all over the place in these nebulae. Pillars are really important. We didn't understand this until we put the Hubble up. You've probably heard of the Pillars of Creation picture from the Hubble. We now understand that this is where stars are born. They're just about to be born. So they're in the tips of these pillars. And when the star cluster is born and it pushes all the gas out from it, The compressed gas that's about to give birth to a star is so dense it's not pushed away. So, it protects the gas around it from being swept away, and it protects the gas behind it from whatever axis it's coming in. So you see all the pillars point in, because the star's protecting the gas behind it. So it's what forms the pillars, and the stars are going to be born out of the tips of these things. So we know that now. And every once in a while you get evidence of that. Here's this called the Elephant Trunk Nebula, and it's just one giant pillar. And here's where the breakout's going to happen at the top. They call it the elephant trunk because the Hubble took a picture, and if you turn it sideways and you squint a lot, it's supposed to look like an elephant with its trunk there. It doesn't look like that to me. It looks like a fist, but the arthritic fist nebula was not a good name for the thing, so we'll call it the elephant trunk. But some people see a gargoyle in this part right here. Once you can't unsee that stuff, but this is one of those pillars, and that's where the stars are born. This is the Heart Nebula, and again, you get this outward flow that just pushes all the gas up. Big star cluster in here, lots of pillars. This is the Soul Nebula. If you have a Heart Nebula, you got to have the Soul Nebula. They're right next to each other in Cassiopeia. Again, but this is cool because you get two nebula forming regions, two star clusters next to each other, two bowls, pillars all over the place. It's a really big nebula. It's super beautiful.
So when they distribute like that, the math distribute, so if you sort of reverse calculate, that's where you get estimates of the age.
Yeah.
Okay. So the estimation of the age of the planets and solar systems are based.
Yeah, and they can look at the spectrum of the star. They can look at its composition, how hot it would be, the radiation coming off of it, and all that stuff. This is the California Nebula. I like this one because it's called Bach globules. That's what happens when the tip of the pillar breaks off and the stalk of it goes away. So you're just left with this ball. This is the Flaming Star Nebula. It's just a big ball of hydrogen. So it's not a big star-forming region, but when I was processing this, sometimes it's really easy to process it. You can process the nebula a lot better if you take the stars away. And then you put them back at the end. But sometimes when you finish processing the nebula, you don't want to put the stars back because it's really pretty. So I did put this one. This is what it looks like without the stars. And you can really see that, well, one star left because it looks like it's illuminating the thing. Here's another example of that. This is called the Wizard Nebula because if you look at it sideways, it looks like a wizard. There's his pointy hat and his nose and his eyeball. Here's his hands, right, and his feet. So this is a sleeping wizard, right? So, and then you take the stars away. So you get a lot better view of the nebula if you take the stars away. It doesn't distract you.
Yeah, yeah.
And then this is the Pelican Nebula, because if you look at it sideways, and it looks like a pelican, but you know, it's. But what I like about this one, here's some pillars, and this one is just about to break out. In fact, nuclear fusion has started. It's blowing out these jets of radiation at its poles, and you can actually see them. You see the little tiny jets coming out this way? Those are called Herbig-Haro bodies, and so you know the star's about to be born. And then you can take them away, and that looks pretty too. So that's the nebula stuff. It's my Cosmos tour. So I'll shift for just a few minutes and talk about how much harder it's going to get for me to do this. But also the impact that light pollution's having, and especially if we consider that everybody's about to turn over to LEDs. Southborough has received a lot of money for green initiatives to help conserve a lot of energy and convert us over to LEDs, but if we're not careful about how we do it, it's going to take all our dark away, but it can also have some serious environmental implications and some implications on human health. If you're a Pink Floyd fan, you remember this, right? So Dark Side of the Moon. Here's what a high-pressure sodium lamp looks like if you split out its light into its respective colors, right? You split its spectrum just like Dark Side of the Moon. It emits light in these really discrete bands. And if you stick around, I've actually got a spectroscope or a couple of them over here, and you can look at a hydrogen lamp like that, and you can see these discrete lines. It emits light. That's very different from an LED. LEDs are broad spectrum. They just spit out lights of light of all different kinds of colors all over the place. Not yet, buddy. After we're done.
Yes.
So it spits out light all over the spectrum. This is what it looks like if you quantify that stuff. So one thing sticks out. Well, two things really. It's that the high-pressure sodium lamps we have, and you know what these look like. They're sort of like these yellowy-orange lamps that we have. They don't have a lot of blue. They emit in blue, but not very much of it. But if you actually quantify how much the LEDs give off, it's this mountain of blue, and that's what's different. For the first time in illuminated human history, we're doing something that's very close to the sun. We're giving off this broad spectrum light that's got lots and lots and lots of blue. So why do we care about that stuff? It's because we've evolved to take advantage of light-dark cycles. We have a circadian rhythm. It regulates melatonin in our bodies, tells us when we're supposed to be sleepy. It regulates all kinds of body functions. And this is what we're going to end up doing to that. Normal blue light signals this stuff to us: waking state, high alertness, more coordination. It's actually the blue light. You've actually got, there's a nerve cluster that runs alongside the optic nerve that goes in the brain. It's called the Suprachiasmatic Nucleus that responds to blue light, responds to light, but blue light in particular is very sensitive. But you don't see with any of that. The suprachiasmatic nucleus is just to detect this stuff. So it just signals to your body, hey, the sun's up, the sky's out, you're supposed to be awake right now. These LED lights were peppering all over the place, right? Certain towns around us, which shall remain nameless, have converted to all these stuff, and it's just blanking light. You've seen this type of light before. It's this first wave LEDs that are just, there's no warmth in the light at all. And we're going to change that bottom part to blue. There have been a lot of cursory studies for nurses that are under hospital lights like this all the time, that work night shifts as well, so they're really messing with their melatonin, that there are particular adverse health effects to this stuff. You suppress melatonin too long, disrupts your sleep cycle, and there have actually been a bunch of scientific studies that say this increases the incidence of disease for us. It's been linked to diabetes, some are correlative links to breast cancer, things like this. So we're still fleshing this out, but it's key that there are manifestations of problems for us in human health. Yeah.
So Destin, when you're talking about the lights, and I'm really just wanting to clarify it, you're specifically, I think, talking about the street lights.
It can be the street lights,
Do you mean,
but these can be ones in your house too.
oh, okay.
Yeah, so if you
And
buy the wrong ones from Home
signs.
Depot. So, yeah, exactly. So it's all of them. And the street lights are the ones that are going to contribute to most of the light pollution with these things. Not too long ago, in June, a couple of years ago, the American Medical Association adopted guidance for this stuff. And so they looked at all the scientific evidence for it and adopted guidance for lighting, and specifically for blue lighting, the different health effects that happen because of blue LEDs. This was their report on the Council of Science and Public Health that they put out. Massachusetts State Legislature is moving a bill through the legislature right now to make sure we establish standards for lighting, that we don't have all this blue coming out and light pollution and that kind of stuff. There was just supposed to be a hearing for this the other day, and so I'm trying to find out how things went. But this is how you'll know it best. If you've got if you've got a cell phone, you've got a cell phone in your pocket, it's got a night shift function on it. You might have noticed that after about 10 p.m. it takes the blue out of your screen. It gets very amber. There's a reason for that, because there's enough study to show that at the very least you're going to mess up your sleep cycle. If you do that chronically and mess with your melatonin, it could have more dramatic effects. So we've got to be careful about all the screens, the projectors, that kind of stuff. To do this, it's not just us, though. For as much as we're affected by this, other animals have circadian rhythms as well. Particularly insects are impacted by this, that are really controlled by light and dark cycles. I didn't just pick a bunch of animals that are cute and would, hit a nerve with you and all that stuff. Not pandering to my audience. These are organisms where in-depth scientific studies have shown that LEDs are having a pretty huge effect on them. You remember when we used to have these? Right, when fireflies were around all the time? Regular light pollution means that they're not playing with us anymore. LEDs are going to start a much larger impact on these creatures. So there's a particularly large effect that we're going to see on the environment, on animals, on ourselves, if we're just not careful about it. LEDs are transformative. It's going to save us gobs of energy. It's going to lower our carbon footprint. We just have to make sure we don't use the wrong lights to do that. Blue light bounces off of structures more, and there's more glare. It has more energy, and so it scatters more. It's one of the reasons why the sky's blue, is because blue light scatters the most. Here's a student on a college campus, right, under one of these lovely LED lights that they put there. Now you see the student, now you don't. The student is still there. Can you see the student? You can't because of glare. The student is actually standing right at the base of the lamp, right there. But it's because the light is glaring right into the camera that you can't see him. Here's another example. Here's a light that has glare. Now, all glare means is the light is not focused where it's supposed to be. It's shining right into your eyes or into your camera. If you just use a hand and cover up the light, you can see there's somebody standing in the fence. They're there the whole time. So there have been a lot of criticism of street lighting and stuff like that. We need to make it brighter. because it's going to keep the crime down. The bright lights are going to help keep the criminals away and stuff like that. Actually, there's not a single study that shows that. In fact, there are studies that show the opposite, because all these lights have increased glare, and you can't see them running around. So it actually could be bad for us. So there are easy solutions to this stuff. You go to Home Depot, you go to Lowe's, and you might flip it around and you see that there are 6,000 Kelvin, 2,000 Kelvin. This is like a correlative color scale for these. It tells you what color the light is, but it refers to how much blue there is in there. And so the really low Kelvin ones are the warm, the amber ones. The really harsh lighting, the bright ones, the blue ones, are the 6,000 Kelvin. They're cool LEDs. We just have to avoid those. That's all you got to do. Let's just not go with those ones. You want to stay toward the lowest Kelvin possible because it's got the least amount of blue. So for your own sake when you buy these bulbs, but also for things that are coming down the pipe, for development lighting, for street lighting, that kind of stuff, for your neighbor's backyard lights. But there's another thing. A lot of the lights in Southborough are very bad. They're these globe lights, right? You see them all over the place, and 50% of the light goes up into the atmosphere is completely wasted. So all the energy it takes to make those photons is just waste. Another 40% or so is glare. That's the stuff that's getting into your eye, and whatever's left is what's shining down on whatever you want it to. So we just have to cover these lights up. This is called full cutoff or full shielded light. It's just simply saying you've got something you want to illuminate, your driveway, your backyard, just illuminate your backyard. Make sure that it's properly shielded so it's not shining into people's eyes or up into the sky for this. A lot of folks have these floodlights in their backyard that sort of shine at an angle. A lot of that light just goes directly into your eyes. If they're shielded and pointed down, you can actually illuminate the yard much better because it's going to look brighter if you take the glare away. And you won't be wasting a lot of electricity, and we get this back. Yay, win for that. So get started. Go to a dark place, better yet, make your place dark. Turn out the lights when you're done with them, right? Don't worry about criminals and stuff. It'll be okay. Go outside and look up. Grab some binoculars and then repeat step 2, because binoculars are a great way to look at the sky. Grab a loaner scope at the library, right? These are great scopes. These are tabletop scopes. These are Newtonian style. They've got great star pointers on them. They actually swivel in a couple directions. You can do these. Are fantastic. You can sit down at your backyard table and do astronomy. Great for all kinds of stuff. I highly recommend these. Take them out and then repeat step 2. Buy your own telescope. Don't forget to return the libraries. Snap a picture with your cell phone. Start with something bright. Moon, Jupiter, Saturn, stuff like that. Get hooked and then do that. Yeah. You can see Jupiter's moons, the Galilean ones, the same ones Galileo saw 500 years ago. You can see Saturn's rings. They're beautiful in a telescope like that. So take them out. Check out the sky. Start simple. The moon never disappoints. Don't look at a full moon. It can actually damage your eyes when you're looking through a telescope. It's that bright. But it also has no features. What you want is a partial moon, because the shadow that's cast through the terminator shines up all the craters on the surface. You can see all these details right near the terminator. It's beautiful to look at a partial moon. Half moon, quarter moon, for that stuff. Jupiter's at opposition. That means the sun is over there, Jupiter's over here. So as soon as the sun goes down, Jupiter starts to come up. It's up all night. It's in the south. It only gets to about 25 degrees in the sky, 20 degrees, something like that. So if you have a clear view of the south, look at Jupiter. It's the brightest thing there. If you wait long enough, you wait until 1 in the morning now, you'll see Saturn come up too. Totally worth it. Sleep is overrated. Unless we talk about LEDs and melatonin, then it's not. Saturn's a stunner. Check it out. You can see open star clusters, double stars. They're beautiful. ISS passes. There was a great one last night. Find out more. There's my website, Stellar Solace. I've got a Facebook page, which is kind of scary for me, but I have a Facebook page. Just search for Stellar Solace, one word. Darksky.org is the International Dark Sky Association. They have gobs of information on all this stuff, pretty pictures, and a lot of great guidance for, okay, I go to Lowe's, which lights can I buy? There are IDA-approved lights that you can look at. Spotthestation.nasa.gov. Susan loves this one. It'll tell you exactly when the International Space Station is going to pass over. Soon after the sun goes down, there's still enough light shining at a high angle that it can illuminate the solar panels on the International Space Station. And every once in a while it passes directly over us every couple of days. And it is bright, super bright, and it's moving across the sky. It orbits the Earth in 90 minutes. You can't miss this thing. It is absolutely spectacular. It can wave to the astronauts in the International Space Station. And most people miss it, right? You're looking down here. It's literally passing overhead, and people are having conversations. Look, there it is. Whoops, I skipped ahead. I do astronomy programs at Chestnut Hill Farm. Sometimes after the farm dinners, we're putting together a standalone astronomy program, and I'm trying to program a lot of stuff. So I'm hoping to get you all out and actually under the stars and do some astronomy with you and join the Natural Sciences Club. We have a great new logo. Here it is. Okay. Cool. I'm done.
We'll take questions if there's any.
Yeah.
I've always sort of worried about this and been afraid to ask anyone. But when you're talking about the stars and all the stuff out there, 300 million years, light years away, how do we know it's still there?
For a lot of it, it's not. So it takes so long for the light to travel to get to us. That's 320 million year old light that you're looking at. So when I took that picture of the Coma Cluster, that's not the Coma Cluster now. That's what the Coma Cluster looked like 320 million years ago, because only that light is getting to us now. So that's one of the mind benders about looking up at the sky. Even if you look, well, I was going to say the sun, but don't look at the sun. When you look at the moon and you look at anything up there, you're always seeing a history picture. It's a picture from the past. The sun is 8 light minutes away. So when the sun's in the sky, you're not seeing the sun as it is now. You're seeing it 8 minutes ago, because it takes the light 8 minutes to get to us. Any of the stuff you look at in the sky is a history book. So that's why we need bigger and better telescopes to build, because the further away we can look, the more we can see the early parts of the universe for that. So it's kind of a mind bender.
It is, but is there anything to make me feel better when I look up?
Other than just be intimidated by that? No. You just got to let it in. Just let it in. Be afraid of it. It's part of it.
Tell how long certain things are going to last. So we know our sun's going to last another 5 billion years. So we know something that's 300 million light years away. We know it's going to last for a couple billion more years. So we're pretty sure it's still there because we can tell how long it will.
And it's cool because the younger galaxies have those nice spirals and everything, but over time when they merge, they lose all that. And so they become these just big balls, those ellipticals in the Coma Cluster. So the further back you look, the deeper into space you look, and the further back you go, the less of those spirals you see, and then you start to see all these ellipticals, and then you start to see these things that don't even look like galaxies. And so we're getting to the point where we can actually start to see what the first formations of these were, because we can peer back so far.
Destin, I think you said you've got some images that took up to 40 hours worth of exposures. So that's certainly over several nights, and you have to do it when the weather is clear enough, right?
Yeah.
So that takes a long.
It can take months to get that much data on it, yeah. And it's with the observatory, there was a couple of astrophotographers that got together. One of them knew how to do coding and wrote some great software to automate the stuff. So it can actually take a picture of the sky. It can tell by the stars in the picture exactly where the telescope's pointed. And then it can look at a picture you took a week ago, and it can park the telescope exactly in that same spot. So that means when I go back a week later to start the data again, it can park it right there again, and it takes the pictures while I'm asleep in my bed with my large melatonin levels, because I have warm LEDs in my house. Yes?
Why do galaxies swirl and become almost flat? Why wouldn't they become round, kind of
Great question. I have to give you a little bit of physics, but it's pretty much all I know about it. It's conservation of angular momentum. So when you start to compact things like that, they start to spin, right? Figure skaters, you notice that as they start to bring their arms in, they spin faster. Sort of a similar effect. That as you start to collect all that stuff together, conservation of angular momentum means it has to start to spin to do that. It's kind of good because it makes really pretty galaxies. And that also means that it starts to collect on a spin axis, so it starts to spread out and become flat, like that. And then two galaxies collide with each other and it messes all that up.
And then there's
So why don't planets get flat, is what he was asking.
Because because those aren't spinning fast enough, right? And there's a lot of density in there. Jupiter is so dense at its core that you take hydrogen, you crush it together so much, it actually takes on the properties of a metal. So it's called liquid metallic hydrogen in its core, so it's just too dense for that stuff. Great questions. Yeah.
Can you hook up a camera to these telescopes?
You can. The easiest thing to do is just park your cell phone right in here. With a Newtonian, it depends. So sometimes the primary mirror the focal length that this has means that if you tried to put a camera on it, if you put a camera there, the chip is going to be about that far back. You can't bring it to focus. That's one of the toughest parts about the Newtonians. Some of them you can, some of them you can't. So it's certainly worth a try. They have an adapter. If you have like a DSLR, it's called a T adapter. They're really cheap. You can get them on Amazon. Instead of putting a lens in there, you put the T adapter, and then it comes with this little piece that looks like an eyepiece, and you screw it into that. And then you just pop it right down in there. And you just try to bring it to focus. So with the Newtonians, it's sort of hit or miss. Sometimes you can, sometimes you can't. If not, you just park your cell phone right in the eyepiece and snap away. It's one of the caveats of Newtonians. They actually make imaging Newtonians where you can't bring them to focus to look through it with your eyeballs, but only a camera can do that. But I would try. These are great. You'll be able to see a lot.
So how long have you had this fascination, and how did it begin?
Great question. My brother had a Tasco gray refractor that he got for Christmas in like 1982. And he never used it, and I did. And the only thing it was good for looking at was the moon. It was horrible. So when I was a kid, I used to look at the moon all the time. And I tried to look at other stuff, I just got frustrated. And so I put it down for a long, long, long time until, like, I don't know what it was, 10 years ago. Yeah. Susan decided to buy me a telescope.
I bought him a telescope.
And
$100.
6 telescopes later, it was, hey, I can use this to take pictures. Not this one, because this isn't good enough. I'm going to buy another one. Yeah. But I still have that one. It's a great telescope.
And he got his brother back. Now his brother is in
right.
business and is buying all these telescopes
Yes.
as well.
Yes. It's good to have friends. But it's just my fascination with space, the night sky. I've always been a space geek. Even though I do biochemistry, it seemed a little bit more practicable. But yeah, I absolutely love space. And it's amazing how much it connects to the stuff that I do. I mean, by day, I do cancer research at WPI. By night, it's astronomy. But when I get into the parts with the narrowband imaging, the chemistry, and spectroscopy, I teach spectroscopy to my students and all other stuff. So I love how they connect.
Do you know where you are if you go in a black hole? Is it like a bag?
If you go in a black hole? Wow. I've never done that. Have you? Have you ever been in a black hole? Take some pictures if you do. I don't know, because black holes, okay, so if you grab a baseball, how far do you think you can throw it? Pretty far, right? Okay. And you throw it, and it sort of goes up, and then it comes back down in an arc, right? It goes whee, and then it comes back to Earth. What if you could throw that baseball so far, it would travel like a mile away, right? It'd just have a longer arc, and it would go around. Now, if you could get that baseball, if you could throw that baseball at 17,000 miles an hour, it would have an arc that matched the curvature of the Earth, and it would just keep going. That's what orbit is. That's why we have to get things moving so fast. A black hole is so dense. It's got so much mass to it. If you try to throw a baseball, it would go thunk right on the ground. If you tried to throw even something really tiny, you can throw it really far, thunk right on the ground. If you tried to move something at 670 million miles an hour, it's still not fast enough to get it to go in orbit. That's why no light can escape. It just sucks it all in. So we couldn't even take a picture. You could take a picture, but nobody would ever see it. Then you'd be spaghetti-fied.
So join me in, let's give Destin one more round of applause here. And we'll be around for a little bit. The library doesn't close till 9, so we have some time if you have any other questions or anything. And Will wants to help you guys take a look at the...
Yeah, I got spectroscopes. If you want to take a look at splitting the
spectroscopes.
spectrum of hydrogen, it's pretty neat.
And also, I just wanted to say a couple more things. So Natural Sciences Club will have other talks like this, other fun things that I mentioned earlier on. But again, you see how we're talking about the natural sciences, but also the impact it has on the community and what we can do as individuals and as a community around the natural sciences. Along those lines, we do have, do you want to mention the signs? We have some... So we have some signs. We're talking about mosquitoes. We're going to do hopefully a talk in a couple of weeks and talking about ways of getting rid of mosquitoes. But right now, so that we don't harm our Southborough environment, we have some no spray signs. If you want to encourage to not have your lawn sprayed when people come through spraying for mosquitoes, being concerned about different diseases. We can talk further about the fact that how the spraying does or doesn't affect those organisms that can carry diseases and how it can have other negative impacts on our environment instead. So if anyone's interested in those signs, we do have them back here. Amy had them put together for us. And was that?
Just about the signs,
Yeah.
just wanted to say it's not sufficient to post the signs, you also have to register your property. It's very simple, it takes only 5 minutes, and we will post information on the Sciences Club Facebook page. Yes, so this is Southborough Open Land Foundation with the local land trust in Southborough, and we're all for the environment and conserving land, and we are encouraging people to avoid spraying their properties.
See this slot? It goes into
And Will is giving, our son Will here is giving lessons on how to use the spectroscope, and you can look up and you can see.
You'll be able to tell what kind of lights these are by looking at
Yeah,
them
if these
through the
are.
spectroscope.
Oh yeah, these are not full spectrum.
No.
They're not full spectrum lights. So if they were full spectrum,
yeah.
it would just look like a full rainbow.
These are fluorescent lights. So this is emitted light. So if you look through the spectroscope, you're going to see defined lines in there. And those are the only colors that they emit. And there's a little bit of blue, not too bad. These aren't horrible. I wish I had an LED.
There's some, we'll pass them around.
But if you, that's
Sodium
oh
lamps
this
are in
no
some
that's a
of the
compact
tunnels.
fluorescent.
Remember the big dig tunnels there? Those are often sodium
Really
lamps,
yellow
very
ones,
very
yeah.
yellow. But if you're a passenger in a car and you have a spectroscope with you, I know it's a lot of things that have to come together, but I've done that. You can look and you can see the sodium lines.
But if you look at an LED, it's just like it was in the picture. It's just no lines. It's just broad spectrum all the way across. So it's emitting light like the sun, and your body responds to it that way. That's an LED, so it should be full spectrum. The trouble with these, there's a little tiny slit that you have to park the light in. It's tough to.
I don't know why it's blind.
Tough to do. Nah, it's okay. Where is it? I can't find it. There it is. Yeah, it is full spectrum. It's just because it's such a tiny light, it just gets a band.
good enough.
Yeah, but you can't. Yeah, you can look at your cell phone lights with those. Got one? Yeah. So I'll turn the hydrogen lamp on. You got to get really close to see it, to see those bands, but really close to it. But make sure you put the light in that little tiny slit. It's kind of tricky, but you can come up and try that out.
Mostly red, but a couple different bands that are there. But thank you all for joining us. And
Thanks so
we'll
much for
see you
coming.
in another